Okay, part two, vertical and horizontal asymptotes. So the first thing is that an asymptote is, I'm going to change this to a medium. An asymptote, first of all, is a spelling. We say asymptote, we don't pronounce the P. I sometimes will try to emphasize the P just so to help my students remember that there is one there. So an asymptote is a line, usually, doesn't have to be, but for our intents and purposes it will be, that the graph of a function approaches as x or y tends to infinity. So if you imagine a hawk coming down and it swoops down and then it kind of levels out as it approaches the ground to grab a rabbit or something like that. Or as an airplane comes in to land on the runway, it comes down and it kind of approaches the runway, it levels out. Now, a plane eventually does touch the runway, but a function will not touch the asymptote. It will just approach the asymptote as x or y go to infinity. So around the origin, it may cross an asymptote, but as x or y go to infinity, the function will not. Okay. The most common asymptotes are either vertical or horizontal, though there are what we call oblique or diagonal asymptotes. In example one, the behavior of f near zero is denoted as, we did this behavior just a few minutes ago, that f of x approaches negative infinity as x approaches zero from the left. What that does is it gives us a vertical asymptote at x equals zero. So what I want to do is, and I'll read this now and then I'll go back and take a look at it. From the figure, you can also see the function has a horizontal asymptote, the line y equals zero. By the way, the line x equals zero is the y-axis, and the line y equals zero is the x-axis. So let's go ahead and we'll take a look back up at the top and see the graph of that function. So we have it right up here, and we can see that if we plot -1, -1, -1, or -0.1, -10, and we get closer, the function is heading off towards negative infinity. So it's going to get closer to the y-axis, but it will never touch the y-axis. And then the same thing from the right. So the y-axis, and quite often what we'll do is we'll use like a dotted line to indicate that there is a vertical asymptote of the function. So again, the line isn't part of the function, but it is a line that the function approaches. Likewise, you can see the graph leveling out. It will never, ever, ever equal zero because you can never divide one by anything to get zero, but we can get close. And so the x-axis is a horizontal asymptote of the function. All right, so let's talk about how we find them. So the definition. So the vertical line, x equals a, is a vertical asymptote of the graph of f if the function goes to infinity, so the function goes up, or the function goes down as x approaches a, either from the right or the left. The line y equals b is a horizontal asymptote of the graph if the function, so the y coordinates, approach b, this value, as x goes to infinity or negative infinity. So here are three examples of graphs of rational functions. And so if we take a look at this first one, we can see that as we get closer to -1, the function goes off towards infinity as x approaches -1 from the left. And as x approaches 1 or -1 from the right, the function goes to -infinity. The function goes down. All right. Likewise, and I'll change color here. Likewise, we can see that as x goes to infinity, the function, it starts off here, the function's at 1, and then somewhere out here, let's say at 1, it gets to be 1.5, and then we're at 1 2/3, maybe 1 3/4, and we just keep getting closer and closer and closer to 2, but we will never, ever get there. So we have a horizontal asymptote of y equals 2 and a vertical asymptote of x equals -1. And so again, usually you can see it, that as the graph kind of does one of these things, it just shoots off towards the top of the screen or shoots off the bottom of the screen. That's a vertical asymptote. And if the graph ever flattens out on the left-hand or right-hand edge, you're going to have a horizontal asymptote. So when we look at this graph here in the middle, we see there's no vertical asymptote. The function never goes off towards infinity. But we do have a horizontal asymptote of the x-axis, which we call, again, the line y equals 0. All right, here, again, the x-axis. So the line y equals 0 would be a horizontal asymptote. And we can see that as x approaches 1 from the left or right, the function goes to infinity. So what we're going to talk about now is how we actually find these vertical and horizontal asymptotes. So the way to think about this is, again, if I have a fraction that as b approaches 0, the fraction a over b gets huge. I mean, think about it. Take if you had one pizza and you divide it among 7 people, okay? We have a certain size slice, but as you shrink the number of people down to 4 people, the slices get larger. And then if you make it just one person, you have the entire pizza. Um, and then if you could make, it's just the idea that as this gets closer and closer, a little bit harder to kind of imagine a pizza done this way, but if you said that you had that one pizza constitutes only half of a slice, that means you would end up with 2 pizzas, which is actually more than what you actually had. I know it's a little bit tougher, but just imagine, I mean, taking 1 and dividing it by this on a calculator, you're going to get 2. And then if you take 1 and divide it by 0.005, you get a much, much larger number. All right. So as b, as the denominator gets closer to 0, the function or the ratio of a over b goes to infinity. So definition of how we find it, let f be a rational function. Again, just a big polynomial. The key is that n and d have no common factors. So if we go back to the example we had before, we had x minus 1 on top and we had an x minus 1 on the bottom. We would have to cancel those common factors first before we address any common factors. So the graph of f of x will have a vertical asymptote wherever the denominator is 0. So to find vertical asymptotes, we start off doing exactly what we did before, which is factor the top and then we factor the bottom. Now, the bottom's tougher because we see we have a 3 in the front, but if you look, 3 goes into 3, 3 is a factor of 9, and 3 is a factor of 162. So that means I'm going to start by taking out a factor of 3, which leaves me x squared plus 3x minus 54. This then factors into x plus 9 and x minus 6. So we see here we do have a common factor of this x minus 6. So what we can do is this, we can cancel them, okay, and say that this is going to equal to x plus 6 over 3 times x plus 9. But we do have to add this little stipulation that x, as long as x is not 6, this is true. Because this value, I can plug 6 into. 6 plus 6 is 12, 6 plus 9 is 15 times 3 is 45, I get 12 over 45. Here, if I plug 6 in, I get 0 over 0. So these functions, they're the same everywhere except at x equals 6. So now, wherever my denominator is 0, it's at that value that we will have a vertical asymptote. So we'll have a vertical asymptote. And I left out a t at x equals negative 9. Okay. Again, expand it out, cancel any factors. Wherever that denominator is still 0 gives rise to a vertical asymptote. Horizontal asymptotes, to be honest, and in some ways they're easier. The process is a little more complex, but it's not difficult. So what we want to do first here is we want to do the same thing, make sure we have no common factors. Then what we want to do is we want to expand them out. So whatever's left, we want to expand out and write as a polynomial. And then what we want to do is we want to focus on the degrees of the numerator and the denominator. So n is going to be the degree of the numerator, and m is the degree of the denominator. And again, real quick, the degree is just the largest power of x. So if the degree of the numerator is smaller than the degree of the denominator, that is, if I have something like an x cubed on the top and an x to the fifth on the bottom, then the line y equals 0, or the x-axis, is a horizontal asymptote. And what I want you to think about here is this. If we start plugging in larger numbers like 10, 100, 1,000, a million, a billion, this fifth power of x in the denominator is going to get so much larger than the numerator that the entire fraction shrinks down and gets closer and closer and closer to 0. If the degrees are equal, then what we do is this. We take the ratio of the leading coefficients of both of them. So what happens here is this, that if n is equal to m, the function will approach that value right there, a sub n over b sub n. And we'll see an example of this. And then if the degree of the numerator is larger than the denominator, the graph has no horizontal asymptote. So let me again, just real quick, show you an example here. If I said this was 7x to the fifth over 4x to the fifth, and again, you have a bunch of other stuff in the numerator and denominator, then 7/4 would be the horizontal asymptote of this function. And lastly, if I had an x to the fifth on top and an x to the third on the bottom, so the degree of the numerator is larger, in that case there, the numerator would grow so much more rapidly than the denominator. They'd get further and further apart, which makes the fraction itself go towards infinity. It's really, really big. Right? So in a case like this, what we want to do is take the function, factor, so I get x minus 4 and x plus 2. In the denominator, I have a factor of 2 and an x. I'm going to take that 2x out, and that gives me an x, and that gives me a minus 4. So we would cancel these out, which gives me x plus 2 over 2x, again, as long as x is not 4. So now we compare. The degree of the numerator is 1. The degree of the denominator is 1. So we are going to have a horizontal asymptote at y is equal to the ratio of these leading coefficients, which is 1/2. All right, we'll do one last video to finish off this packet.